my name is Dana Golden. We're going to pick up now with the basic math review, continuing the introductory lecture to environmental economics. Stick with us if you want. If you feel you're comfortable with Lagrangian optimization and multivariable calculus, totally fine. Just move on to hit the ground running with environmental economics. If not, stay with us. You're paying for this course. Maybe you should get the whole thing. Rate me on Yelp. So derivative function measures how much that function changes as the variable input to the function changes. Common notations include f prime, df dx, and d over dx of f of x. In economics, the derivative is basically all that matters in many situations, because derivatives tell you how the cost changes with the quantity, how the revenue changes with the quantity, how utility changes with respect to goods consumed, and ultimately derivatives and margins are how decisions are made. If you don't have the ability to take a derivative, it's very difficult to solve an optimization problem, which is why derivatives are so useful for economics. As you probably learned in high school or maybe early college, you have the power rule. D over dx of x to the n is nx to the n minus 1. You have the product rule. The derivative of two functions multiplied together is the first times the derivative of the second. The first derivative times the second plus the second derivative times the first. The quotient rule, derivative of a function divided by another function is bottom times the derivative of the top minus top times the derivative of the bottom over the bottom squared. The chain rule, this is very useful if you take my data science and machine learning class, which I will eventually teach. If you have f of g of x, then the derivative is f prime of g of x times g prime of x. Just a quick example using the power rule, which is probably the most common way you'll take a derivative in this class. If you have to, not going to be a very common thing. Just 2 minus 1 equals 1. And then you multiply by 2, 6x, and then x to the first minus 1 equals 0, and then 2 times 1 is 1. F prime of x is 6x plus 2. I reviewed multivariable derivatives, so that was derivatives of a function of one variable. You can also have derivatives of function of multiple variables, which is what makes the economics really interesting and engaging, because it allows you to optimize a function with many variables. So the function f of xy, the partial derivative with respect to x is df dx, and the partial derivative with respect to y is df dy. Partial derivatives show how one variable changes holding others constant. So the important thing to think about this is you're holding one variable constant and taking the derivative with respect to the other. So in this case, you have x squared plus 3xy plus y squared, and then you take the derivative, and it's 2x plus 3y. That's with respect to x. So we held y constant. We treated y like it was just another constant, like it was like that 3 or like that 2. And then in the same one, we take the derivative of df dy. Notice when you arrive with respect to constant, it's 0. So this x squared disappears in this df dy in this derivative. So you're left with 3x plus 2y. The total derivative is if z equals f of xy and both x and y change, the total derivative is dz dt equals df dx dx dt plus df dy dy dt. And now I'm going to talk about optimization, which is like where this becomes important for economics. Multivariate optimization finds the maximum and minimum of a function with respect to multivariable variables, often under constraints. For a function f of xy, a critical point occurs where df dx equals 0 and df dy equals 0. So one thing to remember is, like, when you're doing a univariate optimization, as I'm sure many of you done countless times before, you set a derivative equal to 0, and then you solve for all those points, you run a second derivative test, and now you've maximized the function. In this case, things get a little bit more tricky. Now you have two variables, and so you have really a surface rather than a function. So it becomes more challenging to optimize. You have to think about how the derivatives of the two variables are interacting with each other. So Lagrangian optimization is a tool for constrained optimization. So the goal is to maximize a function of multiple variables subject to some sort of constraint, usually phrased of the form the function of xy equals some constant or some value of another variable. So to create a Lagrangian, you start off with, you add this lambda, and you add this lambda term, which doesn't have to be lambda, it can be any other Greek letter. Economists like Greek, is the function you're trying to optimize plus lambda times the constraint. And so what you're creating here is an ability, by taking the derivative with respect to lambda and also x and y, you're creating the ability to find the constrained maximum of a function. So now you have applied a constraint to a function. So one example here is f of x comma y equals xy subject to x plus y equals 10. I'm going to leave this as an exercise to the reader because I don't have my pen on me, so I can't annotate these slides right now. But basically what you do is you do f of xy equals xy, and then you do lambda times 10 minus x minus y, and then you take the derivative with respect to each of the variables, and then you solve for the variables. Remember, you need as many constraints as you have variables, because you need to have as many variables to solve for as you have free variables. Or else you end up with something that can't be solved for from a linear algebra standpoint. You get linear dependence. We don't want linear dependence. We want linear independence. We're adults, and adults are independent, so we want linear independence. Multivariate optimization is used for economics and utility maximization, cost minimization, profit maximization, and this is really helpful for decision making. So, if you want to maximize a utility function, you have this Cobbs-Douglas utility function, very Cobbs-Douglasy, so Cobbs-Douglasy, you have like 0.5, so they add up to 1, which has all these nice features. So to the budget constraint, you have some goods, you have an income of 12, these things equal 12. You set up Lagrangian, you have your function here, you have your constraint here, and then you have your shadow price of money, which is lambda. Think of lambda as like, if I had an additional $1, what would I do with it? That's lambda. It's the shadow price of money. So step 2, take the partial derivatives and set to 0. So you take the partial derivative with respect to x, and you treat y as a constant here. You subtract 1 from 0.5 equals negative 0.5. Multiply that 0.5 up front, and then you have minus 2 lambda equals 0. Partial derivative with respect to y, 0.5 times x to the 0.5, y to the negative 0.5 equals minus 3 lambda equals 0. And now you take the partial derivative with respect to lambda. This, because lambda is not multiplied by anything, this is always just going to be equal to the constraint. And then now you solve the systems of equations. From Lagrangian derivative of x equals 0 and the Lagrangian derivative of y equals 0, we set them equal together. We get x over y equals 3 over 2. Y equals 3/2 x. So now we have this really nice relationship, which is the really marginal rate of substitution between the variables, which is also coincidentally the slope of the indifference curve. And then we substitute y equals 3x into the constraint, and then we solve for it, and we get 2x plus 3 times 3/2 x. That equals 6.5x equals 12. x equals 2, y equals 3/2 times 2 equals 3. The optimal values are x equals 2, y equals 3. Now we're the optimal level of happy. We are, we're just killing it. We're happy as can be because we maximized our happiness. Maximizing utility results in consuming 2 units of x and 3 units of y. One thing I'll also mention is you don't just have to solve for x and y. You can also solve for lambda. If the constraint is not binding, which it always is going to be in this case because it's a budget constraint, so there's an equality. But if there was an inequality and the constraint was not binding, you would see that lambda would be equal to 0. The shadow price is equal to 0. That's something very interesting to think about, is what is the shadow price and is the constraint binding. We're not going to get into that a lot in this class, and I'm probably not going to ask you to do much Lagrangian optimization. I think I have one problem on homework 5 that might require it, but this is fundamentally a very useful framework to think about throughout the class as to how agents are making decisions and how economics works. Hope to see you next time when we start getting into the real bread and potatoes, real meat of environmental economics, which it's going to be a fun time, guys. Have a great day. See you next time.